Hello, this is topic number 4, Introduction to Basic Electrical Concepts and Circuit Theory for ELE 110, Electronics for Technicians 1. So before we get into the nitty-gritty of the concepts, let's take an overview of the basic theory of atomic structure. On this slide, you can see that we have what's called the Bohr model of an atom. So atoms have structure. Most scientists have come to agreement that the structure is as shown by this diagram. And in the diagram, what you see is kind of something reminiscent of our solar system. There's a nucleus. In this case, there are protons and neutrons in the nucleus, and there are electrons orbiting the nucleus. Now, you may be aware of the fact, excuse me, that scientists have come up with more fundamental subatomic particles and so forth that make up protons, neutrons, and electrons, but it's not necessary to take and study those things to be able to understand how electricity operates and the flow of current and so forth. So the basic atomic components that give atoms their electrical properties are the electrons and the protons. The neutrons are neutral. And again, I say on the slide here, note the similarity of atomic structure to that of the solar system. Electrons orbiting the nucleus like the planets orbiting the sun. So the simplest of atoms, and I make the comment these atoms are the fuel of stars, are basically hydrogen and helium. Hydrogen is one proton surrounded by one electron orbiting the nucleus, whereas a helium atom consists of two protons and two neutrons in the nucleus with two electrons orbiting the nucleus. Now it turns out that there are other forms of these elements, but they're rarer. These are the most common forms of hydrogen and helium. Now if we take a look at the fact we can't see these things, but today our instruments can yield images like this one, which is a hydrogen atom, and this is an atom imaged by a quantum microscope. And actually, all it's showing you is where the most probable position of the nucleus is and the electrons. So it's we can't quite, with the naked eye, see these things quite yet. Maybe that'll change over the course of time. You may or may never had chemistry. So what I've shown here is what's called the periodic table of elements. This is accepted by scientists around the world. And what it does is organize the various naturally occurring and man-made elements. They've been organized into what we call the periodic table of elements by the scientist known as chemist. And you can see it's color-coded here. Turns out the blue is metals, metalloids are the I don't know, gray it looks like, and yellow is the non-metals. So you're familiar with some of these elements. Certainly in column 1A, it starts with hydrogen. We just took a little look at hydrogen. Element number 3 is lithium. Element number 4 is sodium, one of the components of common table salt, sodium chloride. Number 19 is K is potassium. 37 is rubidium, which again, some of these now become not as familiar. 55 CS or cesium, and so forth, make up that entire column. If you go to the far right, that was on the far left, on the far right, we have the inert gases, starting with helium number 2 there, neon number 10, argon number 18, krypton number 36, xenon number 54, and radon number 86. And those are all the inert gases, and they have similar properties. So these things are all organized in columns, and the columns represent their electronic structure. That is the way the electrons rotate the nucleus, and how many there are, and so forth. There's an interesting column 4A. 4A is headed by carbon, number 6. Element C, it's abbreviated as. 14 is silicon. Germanium is 32, and so forth. In that column, we discover our semiconductors, silicon and germanium. And of course, 3A and 5A are important because those are the elements we add to silicon and germanium to make semiconductors and so forth, to make N and P type semiconductors. So these things are all organized again by their chemical structure. And you look at column 1B, that's a very interesting one. It's number 29 copper, number 47 silver or Ag, and number 79 gold or Au. And those are our best conductors. So they have some type of electronic structure that makes them real good conductors. And we'll take a look at that as we go along here. So as I take a look at the next slide, I asked the question, what can we learn from the periodic table of elements? And it turns out we can learn a lot, basically the chemical properties of things. So again, the first bullet, an element's physical characteristics are determined by its atomic structure. On the right, you see a little picture of group 1A, lithium. It looks like, I don't know, slices of meat or something like that. Down below it, it looks like a bologna or something that's being sliced with a knife, and that happens to be sodium. So again, the periodic table is arranged by groups of elements with similar atomic structures. Elements of the same group or column have similar electrical properties and behave chemically in a similar fashion. These elements are very reactive. Lithium and sodium and so forth, potassium, react quite easily with other elements to form compounds. So the next slide shows the group 4 elements, which I mentioned before, and on the picture to the left, group 4A, silicon, that shows a silicon ingot, and what's not obvious there, you have to look, it actually shows a silicon disc which has been changed into ICs on the bottom right hand portion of that. So what would happen is the big ingots get sliced, and it turns out you have like a slice of silicon, and you take and do various operations to it. You can form integrated circuits on the piece of silicon. To the right, we have group 4A. The far left is carbon. The top one is lead, shot. The one to the right is tin, and the one at the bottom is silicon. And again, they're all in column 4A, as shown on the right-hand side there, and they have similar physical properties. And of course, as I pointed out, the silicon on the left is what we use to build integrated circuits, i.e. electronics, basically. So why do these things have these various properties? Well, let's take a look at electron shells and orbits, a little finer detail. So the subtopic here is energy levels, shells, valence electrons, and ionization. So what happens is people are all in agreement with this, that the number of electrons per shell, or energy level, or orbit, if you will, is given by the following equation. The number of electrons, capital N sub E, is equal to 2 times n squared, where n is the shell number. So the first shell, the first possible orbit, and I should expound upon that a little bit more, it turns out that the electrons are only able to organize themselves in certain distances from the nucleus of the atom. So the first shell, where n equals 1, can have 2 electrons, 2 times n squared, where n is 1, gives us 2. The second shell, where n is equal to 2, would be 2 squared is 4 times 2, or 8. So there's 8 electrons in the second shell. The third shell can have 18 electrons, and so forth. Now, on the right-hand picture, you see the nucleus there, and it turns out that to the right of the nucleus is shell number 1, and again, we said there can only be 2 electrons in that shell. To the further on, we have another shell, shell number 2, it looks like, and we see 4 electrons in there, and notice that they have a range of where they can be. Some are closer, some are further apart, and so forth. So that's what happens with the outermost shells. They can have energy levels that have kind of ranges to them. So if we move on from this, we call the outermost electrons the valence electrons. They have the highest energy levels, and they're relatively loosely bound to the atom. The reason why they're loosely bound to the atom is the fact that they're further away. Valence electrons contribute to chemical reactions, bonding with similar atoms, and also are instrumental in determining the electrical properties of the material. They can become free of the atom and its unbound state, and in this rather unbound state, they conduct electricity in the form of a flow of electrons or an electrical current. So again, in this diagram in the far shell number 2, if you heat up an element, it turns out you could take in one of those little electrons could be dislodged from the atom, or maybe if I have a charge that's very high, a positive charge, I could dislodge one of those electrons from the atom. Once they're dislodged, they become available for the conduction of current or current carriers, and again, We'll study that in more detail as we go along here. So let's get to the idea of why the copper atom is such a good conductor. So in this slide, we see a picture of the copper atom. Notice it has 29 protons in its nucleus in the center. It had atomic number 29, you might recall. And then the first shell has 2 electrons, the second shell 8 electrons, the third shell 18 electrons. That adds up to 28. 2 plus 8 plus 18 is 28. So in the fourth shell, since it has 29 protons in the nucleus, it has a single electron in the fourth shell. Now, that would be its valence band. And as stated before, the first 3 shells are capacity. The single valence electron is very loosely bound to the copper atom and can be liberated from the atom through many naturally occurring circumstances that I mentioned earlier. And actually just heat, the fact that we're not at, say, absolute zero. At room temperature, this atom in the, electron in the fourth shell could actually dislodge itself from the copper atom. So another term we want to take a look at is what's called ionization. If an atom absorbs energy from some source, it's possible that valence electrons may escape the atom's influence. This is also known as ionization. So the hydrogen atom is easily ionized, leaving an electron and a proton that are separate from one another. Of course, if they came close to one another, they might recombine. And the same thing with a helium atom, it's easily ionized. So that gives rise to various categories of materials. Depending upon a material's electrical properties, which again is how the electrons are arranged in the orbits, it may be classified as one of the following: a conductor, a semiconductor, or an insulator. So the material's behavior is extremely dependent upon the number of electrons in its outermost shell, which we call the valence shell. If I went back to the copper atom, it would turn out that the material before copper has a atomic number of 28, and it would have 3 complete shells, and it would not be very much of a conductor. It wouldn't. The electrons would be all, the shells would be full of electrons, and there wouldn't be much of an opportunity to dislodge as readily the outermost electrons from the third shell of atomic element number 28. So what makes a good conductor? Typically they have 1 valence electron. And again, copper is shown. And we can redraw the copper atom on the left as the one on the right, where it just shows that if I subtract 28 from the nucleus in the left, I get left with a +1, which is the charge that compensates for the outermost valence electron there. And it takes a look, if you look on the right-hand side, copper, silver, and gold there, the elements in column 1B are good conductors. Again, copper, silver, and gold. Now, most of our wires are made out of copper because silver and gold are so expensive, but at times we have used silver for conductors, and we've also plated things with gold for good conduction. So, best conductors have 1 valence electron, that's column 1B. Best insulators have 8 valence electrons, that's column number 8, and some of the things in column number 8 would be helium, neon, argon, krypton, xenon, and so forth. And you might say, oh, they use neon gas in signs. Well, it turns out if you use enough voltage, you can take and strip those valence electrons away. But what happens in neon gas is that they're very anxious to get back to the atoms, and when they are ionized, they fall back and recombine, and as they recombine, they emit photons, and it turns out the photons is the light we see given off by a neon gas sign. The best semiconductors, as mentioned before, have 4 valence electrons, and they are column 4A, as we already mentioned. So let's take a look at some copper wire examples here. It turns out that if you take a look at the figure or the picture far to the top left, what do we have? We have a roll of copper wire. It's very clean. Has a distinctive copper color to it. It turns out, again, it's the least expensive of the 3 elements that I just mentioned. Copper is used to make wire, which is used to deliver electricity. You might note that early wire was made from iron. Now, if you've gone to some place and had to buy some wire recently, you might argue with me that copper is not very inexpensive, but it turns out it's much less expensive than silver or gold. And there's a couple of rolls of wire to that you might pick up at, say, Home Depot on the right. Gold-plated conductor examples. So these electrical cable connectors are gold-plated. In theory, they're better conductors, but in reality, they resist corrosion better, actually, is their biggest asset. And the gold plating is extremely thin, to say the least, only atoms thick. Some other gold-plated conductor examples, we got a HDMI cable on the left, audio cables on the right, and again, they're also gold-plated. So, what about the semiconductors or the conductors? So this diagram shows a silicon atom top and a copper atom bottom. As can be seen from the diagrams, the copper atom is a better conductor due to the loosely held single electron in the valence shell. The electrons in the valence band of the silicon atoms are not as easily freed from their shell, and actually they prefer to go with other silicon atoms to make up a lattice or crystal, a silicon crystal, because I could share one silicon atom with 4 others, and that would give 8 valence electrons, which would fill that shell, make it feel like it's filled. So electrical charge, this is the basis of electricity. We have things called electrons and protons, and the concept and characteristics of electric charge are that they're similar to magnetic poles, like repels and unlike attracts. So in the diagram there, what you see is if they're uncharged, 2 objects, there's no force between them. If for somehow we could take and charge one of those balls positive and one negative, we'll get opposite charges attract one another. If I could charge both of them positive, they'll repel. If I could charge both of them negative, they will repel also. So attraction and repulsion of electrical charges is what this diagram shows. And again, the scientists of old would actually do these types of experiments with static electricity and could observe this happening, although they didn't talk about electrons and protons at the time. So what happens if I have a force between charges? I create what's called an electric field. So on the left we see positive charge, on the right we see negative charge, and by convention, historical convention, electric field lines are drawn as starting on positive charge and terminating that as the arrowhead on negative charge. So this type of device I'm showing here actually would be a picture of what we call a capacitor. So let's move on. So long time ago, and you can see this guy Charles Augustin Coulomb, who lived in 1736 to 1806. He was a Frenchman, a military engineer. He devoted his time to scientific research when he retired, best known for his work on electricity, magnetism, and it turns out that he is honored today by the electrical charge unit of the Coulomb. So the Coulomb is a unit of charge, and a Coulomb is given by the number of electrons divided by, or the charge rather, is given by number of electrons divided by 6.24 times 10 to the 18th electrons per Coulomb. So if I have 6.24 times 10 to the 18th electrons, or protons it could be, it's 1 Coulomb of charge. Today we can say that 6.24 electrons is a Coulomb because now we have something to represent 10 to the 18th. And this number of electrons came from chemistry. So again, electrical charge, we have ions. We can have positive, negative charge. The diagrams on the left show the formation of positive, negative ions when gaseous HCl, which is hydrochloric acid, is dissolved in water, or hydrogen chloride is dissolved in water, which is hydrochloric acid. Ions are frequently formed during chemical reactions. And again, if we have an ion, it turns out that it means it has a charge. So let me go to the next slide here. Our next thing we want to talk about is we want to talk about basic electrical parameters, which are voltage, current, and resistance. So voltage is defined as a potential to do work per unit of charge. The unit of voltage is volts. So the equation is the voltage is W, work or energy is given in joules divided by Q charge and is given in coulombs. Now, it's a rather abstract equation, not of much use to us. I always like to talk about the fact that the higher the value of V, voltage, the more danger there is to you. And that's probably a good way to think of voltage. You're probably aware of the fact that batteries have certain voltages. Your typical D cell or A cell or AA or AAA cell is 1.5 volts. It's actually more like 1.64 volts when it's brand new. Car battery is commonly called a 12-volt battery. However, it tends to be actually 13.6 volts. The voltage in the house wiring is either 120 or 240, and that's AC, and that's a nominal value of voltage as opposed to an exact. So it turns out that, again, you might want to take and have a more practical definition of voltage. The more charge is separated, the larger the measured, voltage value. Also, the more voltage that one measures, the more potential for doing work. So in the next section, we'll depict ways in which charge may be separated. Depending upon the method, one may produce small or large voltages. Charge is separated by static electricity, but batteries were the first practical way to control the separation of charge. So what is current? Well, current is defined as the rate of flow of charge. So I is equal to Q divided by T. So this equation indicates that current I is given by the amount of charge which passes a given point per second. And indeed, 1 ampere is equal to 1 coulomb per second. Ampere is shown up here, and he again was live 1775 to 1836. So this theory has been around for a long time, but only known by a few people. And now these people like Ampere are honored by naming the unit of current after him. So here's a graphical description of a current flow. And what you see here is that I have a piece of wire, and the wire has randomly drifting free electrons just due to the ambient temperature or heat. So in a copper wire room temperature, there are many free electrons that are in random motion just due to heat. And basically as many go to the left as go to the right. So there's no net current flow. However, if I take, and in this diagram you see plus on the right and negative on the left, if I apply a voltage across that wire, what happens, the positive charge will take and attract the negative electrons. They are, again, the thing that can move. Remember, in a copper wire, what will happen, there'll be so many copper atoms that there'll be sufficient number of electrons dislodged from the valence shell that they can act as charge carriers. So electrons flow from negative to positive when a voltage is applied across a conductive or semiconductive material. And the ampere A, we can show with this diagram where we put a cross section there, and the number of coulombs that pass per second gives rise to the amperage. So the question is, how much current flows if 0.001 coulomb of charge pass a given point in 1,000 seconds? The answer to that would be 1 microampere or 1 microamp. So here's a current example. I'm not going to go over it. I'll allow you to take a look at that. But it has a question, 10 coulombs of charge flow past a given point in a wire in 2 seconds. What's the current? Turns out to be 5 amps. So these examples that I'm showing here may be useful depending upon your prior or lack of prior knowledge about this topic. So if you don't have any knowledge about it, you want to go over the examples. Otherwise, if you know about this, you don't have to. That brings us to resistance. What is resistance? Resistance is defined as the opposition to current. The unit of resistance is the ohm, and it's symbolized by the Greek letter omega. The inverse of resistance is conductance, given by G. On the equation here, G is equal to 1 over R, or the reciprocal of R. So this equation shows that resistance and conductance are reciprocal of one another. Conductance is a measure of how good a conductor something is, a physical thing is. And by the way, the top of that slide was a picture of a resistor, the schematic diagram. So conductance. Conductance used to have a unit of mhos, which is simply ohm spelled backwards, but today has standardized units of what are called Siemens, or capital S, and there's George Simon Ohm and Ernst Werner von Siemens. Two, again, old-timers. Look at the age on those guys, 1787 to 1854, and 1816 to 1872. And again, these were scientists from very old times where they would take and do experiments to learn about electricity. So 1 ohm of resistance or 1 Siemens of conductance exists if there's a 1 amp of current in a material and 1 volt is applied across the material. Now, where do we get voltage? Well, this slide says voltage and current sources. So batteries are, have been around for years actually. And this diagram of a battery cell shows an electrolyte, some fluid, a negative electrode, a positive electrode, and look at the plus and minus above them, and there's a porous separator between them. And it says battery current capacity depends upon the physical size of the battery. And we know that, AAA, AA, and single A batteries are various different sizes. If there is such thing as a single A, I don't know, I think I just misspoke there, but nevertheless, how do batteries produce voltage? They separate charge due to chemical reactions. Different materials used in the reaction generate different amounts of charge separation and hence produce different voltages. So this is simple battery. Now we see batteries here, and I guess there is no just A battery. The D cell, C cell, the AA and AAA, these batteries are all constructed of the same materials and have output voltage about 1.59 volts when unloaded. Sometimes you measure it be like 1.64. All depends if they're brand new or not. So how can we organize batteries? We have several possible configurations. One would be series, the other is parallel. So in series connected batteries, the battery voltages of each cell add up. And so I get a higher voltage. In parallel, I connect them all in parallel, shown on the right-hand side there. So series cells yield a higher voltage, while parallel cells yield a smaller voltage, which is equal to one cell, but greater possible amount of current from the parallel combination. Other sources of voltage. So this is a solar cell. The diagram shows light impinging upon a transparent anti-reflective coating. We have a semiconductor layer, a junction, another semiconductor layer. It's not shown here, but there'd be two different types of semiconductor material, N and P type, and it turns out they produce a voltage when the sun is shining on them. The sun's energy provides a means to separate charge. If you want to see more details about this process, do a YouTube search, and you'll see all kinds of videos about this. Other sources of voltage, generators. Mechanical energy is used to separate charge in a generator. This is due to what's called Faraday's law, i.e. the generator effect of passing a wire or conductor through a magnetic field will induce a current in that wire. So what I've got here in the next few slides is a generator simulation kind of, where what I'll do is show this is the first 90 degrees of the turn and produces the first quarter of a sine wave. Here's the next 90-degree turn, produces the rest of the upper portion of that sine wave. Now it moves again. We got 270 degrees of rotation. I've got 3/4 of the sine wave, and it moves one last time back to where it originally started, and I've got an entire sine wave generated. So this type of generator produces an alternating current, an AC sine wave. Where else can we get power? Well, power supplies convert AC voltage to DC voltage. It's more efficient to transmit AC power, but it must be converted back to DC. You'll probably hear more about that, or maybe you have watched actually the Discovery Channel's series about the Edison-Tesla war of the AC versus DC. So I show you a couple of power supplies there in the bottom, and today in some instances it's been found that DC transmission electricity is more efficient than AC transmission. So it turns out over 100 years of transmitting AC, now we're going back in some instances to DC, again being more efficient. But usually what happens, you take and plug a electronic power supply into the wall, and these power supplies I show here can give you whatever voltage you want on the output. You can take and set the output voltage. An ideal voltage source. What's an ideal voltage source? It can provide a constant voltage for any required current. Does such a device exist, I ask? And of course, the answer to that question is no. Anyone who's lived in New England and goes out, maybe starts their car in the cold weather, knows that the cold kind of saps the voltage of the battery. So voltage source symbols, you might be familiar with these. A battery on the left-hand side, V sub S, voltage source with a plus and minus. And notice the symbol for the battery is a couple cells, and that's what battery actually stands for. Battery stands for the combination of cells of a single cell that would generate electricity. On the right-hand side, we see a circle with an AC symbol, a sine wave symbol inside. That's an AC voltage source. These are the symbols typically today that we use to represent simple voltage sources. So one that you don't find too commonly, but we talk about it in electronics, is a constant current source. And it's shown as a circle with an arrow in it. And usually what will happen is the amount of current would be listed next to that circle. The constant current source provides a constant value of current regardless of the load. Constant current sources are not commonly found in a lab. And it turns out that, again, doesn't matter what you attach to the thing, but that's what makes it kind of crazy, because I could put a 1 mega ohm resistor, and if I had a 1 amp constant current source, I'd be producing 1 million volts across the 1 mega ohm resistor, which most likely would fry the resistor. But again, we sometimes have these ideal sources to model what's going on over limited ranges for, say, in this case, semiconductors actually is why this thing was invented. So now we have a picture of resistors, and again, the symbol up to the top there, the value of resistor will be listed, and you can see carbon composition with the printed bands of colors on them, a metal film chip resistor in B there, chip resistor array in C, a resistor network in D, a resistor network surface mount in E, and a high-powered resistor shown in F. So as you can see here, there are many different physical implementations of resistors. A little more detail of these. It turns out the old-fashioned resistors, A there, it turns out there was resistance material, some carbon composition with glue and so forth, carbon particles and glue, and 2 leads going into the thing, and they would try to take and make the resistance equal to what it would say on the color bands. A more modern resistor is B, a cutaway view of a tiny chip resistor, and a protective glass overcoat, ceramic substrate, and a resistive material that we take and can diffuse onto that surface and do it very accurately. Here's another picture of resistors. They're known as metal film resistors. They're very popular when through-hole technology was used to make printed circuit boards or PCBs. Today they're not as popular. You'll find them in our lab, but that's about the only place. If you look on a printed circuit board made in the last 20 years, you won't find any of these resistors. They're pretty colorful though. So here's more details about a typical film resistor or resistor network. The resistor color code we talk about, but we try not to harp on it because, again, you don't find these things anymore. So traditionally, resistor values have been marked on the body of resistor by a color code. If one does an internet search, one can usually find a resistor color code calculator. So you go to Google and you say, okay, what's the value of such and such a resistor? You list the colors of the various bands, and it'll come back and tell you. Or if you want a certain value resistor, you plug it in, and it'll tell you what color it should be. So here's the color code. I'm not going to go over it too much, but the digits in the first 2 color bands are digits. They have black, brown, red, orange, yellow, green, blue, violet, gray, and white to go from 0 through 9. The tolerance is the 4th band. The multiplier is the 3rd band. It doesn't have this slide. Most resistors now are 5% or better with a gold tolerance, and it turns out the number of the multiplier, for instance, if I had a red 3rd band, I add 2 zeros to whatever the first 2 bands are. So here's some examples, and I'm going to not go over them, but you should go over these to make sure you're understanding what the color code is and how it works. If I have a 5th band resistor, sometimes used to indicate the reliability of the resistor or failure rate, often a mil spec or military specification for the resistor, and they would be very expensive resistors. So this slide shows you surface mount technology. Surface mount resistors are shown here, and they're very small. This has been blown up. There are variable resistors, and variable resistors allow you to get a resistance that you want to take and change. So these things are called potentiometers and rheostats, and so they show a basic construction. There's a resistive element. You see the 3 schematics where there's 3 terminals. There's from 1 to 2 is the resistive material, and number 3 is a wiper, it's called, that can take and adjust what resistance you're tapping off of. If I connect 3 to either terminal 1 or 2, I form what's in the middle there, B, a rheostat, and it's showed in part C, potentiometer connected as a rheostat, which I just mentioned. So some of these, what they look like, typical variable resistors, they are ganged here, a few of them. The top row has, there's one on the far right, the square ones, that's 4 variable resistors ganged together, so they all turn simultaneously. Then to the top picture there to the left is a 3-gang, and then a single-gang potentiometer. These types of components are going the way of the dinosaur. They're being replaced by digital versions of potentiometers. Consider your favorite, your TV remote control and the volume control. That's all done digitally. So you take and press a button, and what happens is it takes and applies a different voltage to a device whose resistance, could say, varies with how long you hold the button on the volume control. It's a little more complicated than that, but let's leave it at that. So this kind of shows some other potentiometer characteristics. In this figure, I show a linear, which means if I have a quarter turn, I get a quarter of the resistance. If I do a half turn, I get a half resistance. 3/4 would be 3/4 of resistance. So that's figure A, linear. Down below it here is figure B. And this one, notice a quarter turn does not give me a quarter of resistance. Half turn does not give me a half. These are logarithmic. Since our hearing is logarithmic, we often use this type of potentiometer for volume controls. And again, unless you got something real old, a piece of old equipment, it turns out that you won't have knobs on it anymore. You'll have a remote that'll take and raise or lower the volume. Next slide is thermistors in photoconductive cells. For the laser people, a thermistor is sensitive to heat. Its resistance varies with temperature. And I should say for laser people here, a photoconductive cell has a varying conductance with light intensity. So the two symbols, the thermistor is part A, part B is the photoconductive cell. And if I go and take a look at this slide, what do I have? I've got a Arduino application. The Arduino is on the left. I've got the Arduino set up with some type of sensor. Well, the sensor's in the little proto board in the far right, a thermistor, and it turns out that I can display the temperature as read by the thermistor of 28.88 degrees centigrade. And it turns out these things are extremely accurate at this point. So here's a couple of thermistors in photoconductive cells. Photoconductive cells use a window to expose the device to light, and it turns out that you might find this in one of an oil burner or gas burner that detects the flame or lack of a flame as a safety device. So these again are very common types of electronic devices. So here's a review of electrons. I'm not going to dwell on this. Select the following value resistors from up above. So it turns out that you'd have to go back to the color code to do this. So let's skip over this and get to the basic electric circuit. So here's a basic circuit. There's a graphical picture on the left-hand side and a schematic diagram on the right-hand side. So the basic electrical circuit consists of a source, a load, and conductors to carry the current. So figure 228 here shows a battery, shows wires connecting a lamp. So that's pretty self-explanatory. On the right-hand side, figure 229 shows the battery symbol and the lamp symbol and two conductors for wires to connect to it. So it turns out that would be an electric circuit. And we'd call that a complete circuit because there's no break in the wires. There's a path for the electrons to flow. So this next slide talks about closed or open circuits. And what do we have? We have switches. Switches are used to control the flow of current in a circuit. And everyone's familiar with the switch on the side of a wall where you turn lights on in your home or apartment or whatever. So this one shows the graphical on the left-hand side. The switch is on, the light's on, and it shows the closed switch to the right. The bottom diagram shows the graphical picture when the switch is off, and it shows the open switch schematic down below in the bottom right-hand corner. By the way, I say note the direction of current flow. This is called conventional current because it looks like the current comes from the plus side and goes to the negative side. Now we know that's not the case. So there's a difference between what's called conventional current, the old-fashioned way of looking at things before people discovered it's actually the electrons that do the current flow. So they're also called complete circuits when the switch is closed. Okay? So what about this conventional current flow versus electron flow? Well, I always blame Ben Franklin. Supposedly in about 1752, he made a choice that conventional current flows from positive to negative. However, we know electron flow is actually negative to positive, what's really occurring. And the practical implementations of this, it doesn't really matter. Text may show either conventional current flow or electron flow or both. It can be confusing to people. The military used to love to use conventional current flow, and I had some students that had gone through the military training, and they would argue about the electrons were going to conventional current. But we know electrons go from negative to positive. They're the ones that move in the wire. So more complex switches. In this diagram, we see a switch on top left here, which is connected to the battery and two different lights. And it turns out that switch can actually determine which light gets turned on. The schematics to the right of that graphical pictorial circuit show if it's in position 1, lamp number 1 gets turned on. In position 2, lamp number 2 gets turned on. So that's an example of what's called an SPDT switch. And an SPDT is single pole double throw. So it can control the flow of current to 2 lamps and many different types of switches. So here's a bunch of them. Not going to go over them too much, but the schematic for a single pole single throw is the original switch we're introduced to. Now a single pole double throw. There's a double pole single throw, a double pole double throw. And other switch symbols are normally open push button switch. For E, F is normally closed push button switch. And if you push on those things, the first one, E, would make a contact, but it has a spring on it, so if you let go of the button, it disconnects. The normally closed push button has a spring. If you take and push on it, it'll disconnect, but if you let go, the spring will bring it back, so it's making contact. And then they show a single pole rotary 6-position switch there. Today we call these electronic multiplexers for the rotary switches. More switch details here. I show a bunch of different switches. They take on many different physical forms. And we know switches can wear out. Semiconductor switches don't wear out. They can fail, however, so they're preferred over these mechanical switches whenever possible, or wherever possible. Mechanical stuff wears out. Analogy that to the computer world would be a hard disk that can crash versus a solid state disk, which is made out of semiconductors, not a mechanical like a hard disk, and it can't crash. Can fail. You always want to know if it can fail. What's inside a switch? Basically this. You might note the mechanical instruction with the wear points on this. So as you flip it back and forth, it actually causes that piece of metal in there to flex one way or another, either close or open the connection. Now, that brings us to protective devices called fuses. There's a picture, a bunch of different fuses. There's a symbol down there to the left of my headshot here, the fuse symbol and the circuit breaker symbol. So fuses actually take and destroy themselves, okay? And to protect electrical systems, we use fuses or circuit breakers. The fuse burns out, you got to replace it with another one. They are designed in a way so that excessive current is drawn by system due to a component failure normally. They will, or a short circuit, they will open up and stop the flow of current. Fuses cannot be reused. Circuit breakers, on the other hand, respond to an overflow of current with a magnetic structure that actually takes and causes the circuit breaker to break, but then you can reset it. And again, there's all kinds of pictures of fuses up above and circuit breakers down below there. What about wires? Conductors, in other words. Wires have existed for over 200 years. Recall the telegraph was invented in 1836. The early telephone system used iron wires because it was cheaper. Today, most wires copper or copper coated and usually covered by an insulator, plastic coating. In a circuit, a wire is considered to be a perfect conductor with zero resistance. Early resistors were constructed from lengths of wire. If I had a length of wire 10 feet long, it would be a certain resistance. A length of wire 20 feet long would be twice the resistance. This is a picture of New York City back in the late 1800s. There were many telephone electrical wires. It looks like a big mess. They were eventually buried underground with the subway system. That's how they got rid of them. You go to New York City, it's not like this. All the wires are underground. Of course, being underground, they're subject to the possibility of problems being underground. You may recall that a recent hurricane took in some of the water went into a subway system, and a lot of electronics and telecommunication stuff was burnt out by the water, especially salt water. It's terrible for electronic stuff. So wire characteristics. Wires vary in diameter but conform to standard gauge sizes called the American wire gauge or AWG. The larger the AWG number, The smaller, thinner the wire, that seems backwards to me, but wire sizes are given in terms of cross-sectional area. This measure is called the circular mil, or cm. So here's an AWG table. The area in circular mils is given by this equation. The area is equal to diameter squared. So some of the wires that, notice they ran out of digits. So the smallest wire is 40, which is thinner than human hair. And 1,000 feet of that wire actually has 1,049 ohms of resistance at 20 degrees Celsius. If you go down to size gauge 1, you see it has a certain size. But there's also gauge 0, then there's double 0, triple 0, and 4 zeros. They call that double aught, triple aught, and quad aught. And again, it turns out that they are very large in diameter. In a particular residence, a house or apartment, you'll have size 12 or 14. If we take a look at the table, size 12 has resistance of 1.588 ohms per 1,000 feet. You hardly ever have any runs of wire that long in a house or apartment. So basically, you can say that the connection is like resistance free. And size 14 wire has 2.525 ohms per 1,000 feet. Again, 20 feet of that wire has a very low resistance. So there's very little voltage drop across the wires that are in residence wiring. So we continue on here and we look at wire resistance. How we figure out wire resistance is by this equation. And any wire except a superconductor will have resistance. The resistance is proportional to the length, the wire's resistivity, and inversely proportional to its cross-sectional area. So resistance is equal to rho, which is resistivity times the length L divided by the cross-sectional area A. And continuing on with this, here's a wire resistance example. I'm not going to go over this, but you can take a look at it and you'll discover that, this gives you a value of 100 feet of copper wire with a certain cross-sectional area. Now, the next topic is grounds. Ground is very important for safety purposes. Ground's a reference point in the circuit, has a potential of 0 volts. There's a safety aspect of it. Earth ground is commonly used by the utilities, the electric, the telecommunications. If you have a cable TV, that cable will be grounded as it comes into a house or apartment. Your wiring, the neutral wire is grounded. Electronic equipment often uses a chassis ground, which may or may not be connected to earth ground. A car uses a chassis ground. All the metal in the car is 0 potential. Grounding is an important safety consideration I mentioned before. So here are the ground symbols that commonly are used. The one in A is kind of old-fashioned, B is a little more modern, and so is it C. Grounds are a common point. So the little diagram here that I'm hiding a little bit with my headshot is a battery and a lamp. And notice that they're connected together by a common ground. That could be the chassis. So I take the negative side of the battery and attach it to the metal of the chassis. I connect one side of the lamp to the metal of the chassis, and the chassis forms the connection between the battery and the light bulb in this case. So you can have a common ground. So I kind of digress here. Residential outlet wiring. It turns out that we should take a look at this because you might get the wrong impression taking electronics. I say, note that unlike electrical circuit conventions, the hot lead is black and the neutral or ground lead is white in AC power wiring. You may know from lab experience that red is positive and black is ground for electronics and for a car. But in your house wiring, residential outlet wiring, this is what it looks like. Now there's also the green wire. That's a secondary ground. So what happens here, this shows how you'd wire stuff. This shows 2-wire Romex with a ground. So 2 wires are the black and the white, and the ground is the green one. And what happens, the greens all get connected together and go all the grounds, as well as the grounding point of the box. The outlets have an important aspect to them. The longer slot is the neutral or ground. The shorter slot on the right-hand side, both of these outlets here, is the hot lead, and notice blacks go to them. So it turns out that, and this is rather interesting, okay, yeah. It turns out there's a connection between the 2 wires, 2 screws on the left-hand outlet. So what we're doing is we're taking and jumpering the black lead that comes in from the wire, the Romex, over to the right outlet. And notice we use wire nuts, these plastic nuts on the green and the white to take and make the connection and keep them insulated from the rest of the world there, so we don't have any shorts. So that's residential outlet wiring. And here's a little more detailed look at how, you have an outlet or breaker box, it's called, in the top left, and you have 240 volt circuits, 120 volt circuits, and it shows various things like the 240 volts might go to an electric water heater. You might have a 60 amp sub panel. They use the size of wire there, 6.2 they call it, or 10.2, different wire sizes. 12.2 is a 20 amp circuit. 14.2 would be a 15 amp circuit. They show the outlets, the switch, the boxes for lights, dedicated outlet for a microwave there. You wouldn't need that anymore. Microwaves usually don't need dedicated circuits. Power vent water heater would plug in and so forth. And it turns out that we kind of set up different circuits with our breaker box for safety concerns and to isolate those circuits if need be. So if you want to make basic circuit measurements, it turns out we want to measure, say, voltage, current, resistance. They're commonly required to deal with electronic systems. So at one time there were voltmeters, ammeters, and ohmmeters. Today these functions are all combined into a single instrument known as a VOM, which would be a volt-ohm meter, or multimeters, usually analog, or digital multimeters we call DMMs. So DMMs are typically used today. Some people call them DVMs. So here's some old-fashioned ones. On the left is an analog meter. It's all but obsolete. On the right is a digital meter. The cost of a DMM today is so low it makes very little sense to purchase an analog meter anymore. The DMMs will give you a digital output reading. Typical meter symbols are shown here. A bar graph, a digital meter, a needle, or just a general symbol. So popular software products like Electronic Workbench, which we call EWB, Multisim, Circuit Maker, and Tinkercad, used for circuit simulation, use similar symbols. So it turns out that very often these are what the symbols you'll see for a meter in those simulation programs. Now, how do you measure current? Current is measured by breaking the circuit. So I have a battery and a resistor here, and I'm connecting through alligator clips the battery to the resistor. I have the schematic diagram shown on the right-hand side, which is showing conventional current flow. What I have to do to measure the current is to disconnect one of the leads. I can open the circuit either between the resistor terminal or between the resistor and negative terminals of the source. And what happens is now I have to take and put a meter in there. So this shows a graphical diagram where I've broken that circuit. I put the meter into the circuit. To measure current, you must have the current go through the meter. So again, measuring current requires the current in the circuit flows through the current meter. It's the only way you can measure it. There are some clamp-on ammeters. Anyone out there listening to this might say, oh, I have a clamp-on meter. Well, the clamp-on meter measures current by measuring a magnetic field around the wire. A little bit different. To measure voltage, I can put the voltmeter right across a component or in parallel with a component. And this shows the schematic and the diagram of doing that. To measure resistance, I have to take the component out of the circuit because it turns out the meter actually acts now as a source of voltage, applies a voltage to that resistor, and measures the current, translates it into a resistance. So in measuring resistance, the component must be disconnected from any power sources. It doesn't have to have both leads. You could disconnect one lead and have the resistor hanging there, still connected, but it's got to be disconnected from the power source. Reading analog meters. The scales of an analog meter are not easy to read, so I'm going to skip over this because basically we wouldn't want you to be learning old skills. You can take a look at this if you want, but notice that you have to figure out what scale is being used, and sometimes they would have a mirror backing, so you get rid of the parallax problem. Digital multimeters look like this. Fluke is a major manufacturer, and they work quite well. How do they have the display? Basically, use 7-segment display technology or some variation of that to take and put the digits up on the meter. So it turns out that they might use an LCD display as the other one. So here's our present digital multimeter resolution, and you get accuracies in thousands of a percent. They're quite practical matters. So here's a basic automobile panel illumination circuit schematic. Shows a battery, a fuse to protect things, a switch, a rheostat to vary the current going to the lamp so we can dim it. So let's see how we might implement the circuit in the lab and then make circuit measurements. How we'd probably do it is put a proto board here. We get a typical bench power supply. We'd have our meter. Simulating the circuit with Tinkercad will yield the same basic measurements and give you a pretty realistic picture of what you're doing. Proto boards, we just touch on them. Again, how they're organized is that the columns here vertically on the top and bottom of that separation in the middle are connected together. So anything connected in one column here are all connected together. What happens going the opposite way is they are connected horizontally on the outside of the probe. So again, to measure current, we must break the circuit and insert the current meter into the circuit to measure the current that's flowing. This is easier using Tinkercad actually, but this diagram shows how we'd set up the proto board to do it. Measuring voltage, we can measure right across something, so we don't have to disconnect anything. That's pretty easy. Measuring resistance, we have to take and disconnect the component. So the summary of this chapter, zero symbols, you should be pretty familiar with now. A battery, resistor, potentiometer, rheostat, lamp, and ground symbols. All the switch symbols, fuse, circuit breaker, voltage source, voltmeter, ammeter, and ohm meter for, again, measuring. So, summary. Measure voltage across components. Measure current through components. Measure the resistance of a component without any supplied power. And that's it for this presentation.